now the objective is not just to solve the initial value problem, but also to determine where the solution attains its minimum value. Right? So what I'm going to show now is that it is better to solve the second part first, and then to solve the initial problem. Okay. So in other words, I'm going to show that it is possible to attains its minimum value without actually solving the initial value problem. Right. So what do I mean? Right. So you know that remember that if we have a function y of t and we want to find its minimum value, how do we do that? So to do this, we just find y prime of t and equate it to 0. But even y prime of t, right? So y prime of t is 2y squared plus xy squared. This is equal to 0. Now we can take out y squared, so this is 2 plus x times y squared is 0. And so in order for this whole thing to be 0, either y is 0 or 2 plus x is 0. No? So 2 plus x is 0. So which means that x equals negative 2. Well, at the same note, if x is less than negative 2, then the left-hand side, sorry, the right-hand side of our differential equation, is 2 plus x times y squared. And 2, if x is less than negative 2, then 2 plus x is negative, and this whole thing is negative. Yeah? And if x is bigger than negative 2, then the right-hand side of our differential equation is still 2 plus x times y squared. Now 2 plus x is positive, and y squared is positive, so it is positive. So it means that if x is less than negative 2, then since the derivative of the unknown function is negative, it means that the unknown function is decreasing. And if x is bigger than negative 2, then the unknown function is increasing. Right? But then when the unknown function, it was decreasing, so until the line x equals negative 2. And then at x is negative 2, its derivative is 0, and then it starts increasing. But then you can see that clearly when x is negative 2, we have a local minimum, right? So therefore, the solution attains its minimum value at the point when x equals negative 2. So x is equals negative 2 is the answer to the second part of this problem. So note that, and it is important that we were able to figure that out without explicitly solving the initial value problem. Well, but still we have the objective to solve the initial value problem, so let us do that. To do that, we rewrite our differential equation using dy and dx equals 2 plus x times y squared. I've already done that. So now we are moving everything with x to the right and everything with y to the left. So dy over y squared equals 2 plus x times dx. Then we are doing integration. Then the antiderivative of 1 over y squared is minus 1 over y. The antiderivative of 2 plus x is 2x plus x squared over 2, while plus some constant. Now, the next step is to find the constant. Well, as a matter of fact, here it doesn't really matter when you find the constant, because it's really easy to solve for y here, but it is just a good habit to find the constant first. So how do we find the constant? We let x be equal to 0 and y be equal to 1, as in the initial condition. So minus 1 over 1 equals 2 times 0 plus 0 squared over 2 plus constant, right? And so constant is negative 1. It's very easy here. So now let us just substitute it to the equation. Minus 1 over y equals 2x plus x squared over 2 minus 1. So then y is going to be minus 1 divided by all this stuff. So x squared over 2 plus 2x minus 1. Well, and then you can simplify a little bit if you want, so you can multiply by both numerator and denominator by 2. So we're going to have minus 2 over x squared plus 4x minus 2. This is the answer. This is the answer to the first part. By the way, notice that if we found this first and then try to figure out where it attains its minimum value, we would have to differentiate this whole thing, and this is kind of a bit, I mean, it is of course doable, but it is harder than doing it without solving the initial value problem. Okay, so this is the answer to the first part.